Hello, I've been asked to give you a talk about geoscience, about what geoscience is, about what we can do with geoscience, and just as importantly, what you can do, what you will go on to do as a student in geoscience. Now, my name is Matthew Genge, and I am a senior lecturer in the department. So I will be standing up and teaching you a lot over the next 3 to 4 years. And my own speciality is in Earth and planetary science, especially the study of meteorites. So you're going to have to forgive me that my view of what geoscience is often involves outer space. Now, really, if you'd asked me 30 years ago and what geoscience was, I would have said, well, geoscience is the study of the Earth. It's the study of how the Earth's interior, how its interior processes affects the biosphere and the hydrosphere and the Earth's atmosphere. It's about Earth history, and it's about the resources that we can get from the Earth. But actually, that all changed in about 1983, because in that year, some scientists working in the Antarctic found an amazing rock. And the rock was a meteorite that came from the planet Mars. And all of a sudden, we now had samples from another planet by which we could look at the geoscience of another planet. So all of a sudden, geoscience stopped being just the study of the Earth and became the study of planets in general, because rocks record history. They record the past events and evolution of planets. And actually, as a definition of geoscience, even that's not good enough. Because amongst those meteorites that fall on Earth, very few of them come from Mars. We've got around 80 meteorites from Mars and about the same number from the Moon. And interestingly, those meteorites look identical or almost identical to the Apollo mission samples. So NASA really did go to the Moon. The evidence is in the rocks. But actually, most meteorites don't come from planets at all. Most of these rocks come from either asteroids, or potentially some come from comets, especially tiny little dust particles, which is made out of rocks that are still rocks that fall on Earth all the time. So actually, we need to say that geoscience isn't just the study of planets, it's the study of planets, moons, asteroids, and comets, all those objects in our solar system that consist of rocks that geoscientists study. And actually, even that's not a very good description of what geoscience is. Because amongst the rocks from asteroids and comets, they contain some mineral grains that actually predate our solar system, when our solar system looked like this. And these are images from the Hubble Space Telescope of part of the Orion Nebula that show baby stars. And this is what our solar system looked like 4.5 billion years ago. In the middle, we've got the baby star, and then surrounding it is this disk of dust and gas. And it was in that disk that small dust particles stuck together to make larger particles, which stuck together to make fist-sized pieces of rock, which eventually stuck together to make planets. This is where the whole business of planets starts. And some of the dust grains that were the mineral grains we find within meteorites were those original dust grains. And some of them have such unusual compositions, and that's isotopic compositions, that they cannot possibly have formed within our solar system. They had to form where you make elements, which is in giant stars or within exploding stars such as supernovae. So actually we have to say that the study of geoscience is actually the study of planets, moons, asteroids, comets, supernovae, massive stars, planetary nebulae, and actually even the interstellar space through which all these dust grains had to travel in order to form our solar system. Now, really, my point in telling you this is to show you how much geoscience has changed. 30 years ago, you went to university and you studied the Earth. Now, we study almost anything in the universe, anything with rocks, and that's an awful lot of stuff. So I hope you can see that geoscience has expanded massively. It's a very young subject. There is more to learn in geoscience today than ever before. And really, we can break geoscience or geoscientists up into two different groups, the geologists and the geophysicists, and both have a different approach. So geologists, and I am actually a geologist, geologists start by observing the natural world and then make interpretations, often interpreting the past, but sometimes in order to predict the future. And this is a really good example of what geologists do. This is some rocks from our Sardinia third-year field trip. These rocks are around 400 million years old. And I hope you can see that actually there's two different kinds of rock here. There's these rocks below this line, and they contain lots of rounded pebbles. It's a rock known as a conglomerate. Whereas above, there are these grey rocks, which look pretty homogeneous, but if you've got your face really close to those rocks and had a good look at them, and geologists frequently do have their noses right up against rocks, you would see that that grey rock contains lots of sand grains and is a sandstone. And just this combination of layers of pebbles and layers of sand tells us what the environment was like 400 million years ago here in Sardinia. It was an environment covered with braided streams, streams with multiple channels, which were bringing in floods of pebbles and floods of sands into valleys in an uplands region. So using nothing more complicated than my eyes and some knowledge, I can do this detective story and interpret what the Earth used to look like. And actually geologists can do better than that. So you can probably see that there is a contact between the sandstone and the conglomerate, the rock containing pebbles, and that actually the biggest pebbles are up here at the top of the layer, and the little pebbles are at the bottom of the layer. So the size of pebbles decreases downwards. But if we look in a modern river, we dig a trench in a modern river, we can see that each layer usually has the largest pebbles at the bottom and the smallest pebbles at the top. And it's very easy to understand why. A big flood of water comes in, bringing in all these pebbles of different sizes, and as that water slows down, it's the largest pebbles that drop out first. And the real importance here is this variation from big pebbles to small pebbles tells us that that way is up. But over here, it looks like this way is up, that these rocks are upside down, which is clearly ridiculous. However, you can turn rocks upside down. If you take a huge slab of rock and you squeeze it enough from either end, it will fold, and part of that fold can turn upside down, can be overturned. And here in Sardinia, those slabs of rock are around 10 kilometers long by half a kilometer wide. Just imagine the amount of force that you require to turn over a slab of rock 10 kilometers long by half a kilometer thick. And these are the forces generated when continents collide with each other and make mountain ranges. So using nothing more complicated than my eyes, a geologist can look at these rocks and say these were trapped between two continents and formed part of a mountain belt at some time after they were deposited 400 million years ago. So geophysicists do something a little bit different. They approach geoscience in a different way. Geophysicists are much more interested in understanding the natural world in terms of fundamental physical laws, often through numerical models of the natural world. And usually these models are to try and predict the future. Now, a really good example of the kind of activities that geophysicists do is in predicting earthquakes. So this map shows San Francisco, the San Francisco area. It's a fancy 3D map. So Alcatraz is over here, and the Golden Gate Bridge is just there. And on this map, you can see these stars plotted, and these stars represent the sources, the epicenters of large earthquakes. And I hope you can see that most of them line up along these red lines. And these are fault lines or fractures in the Earth's crust. And it's movement on faults that generates earthquakes. But not all faults produce earthquakes. Some faults can gently move and just creep. And as they move, they release stress. So the stress cannot build up along these faults, whilst other faults stick and the stress builds up until suddenly they fall and they suddenly fail. And it's that sudden failure that generates earthquakes. So what geophysicists attempt to do is calculate how the stress moves through the crust and where that stress will build up to generate the next large earthquake. And it's not just in fancy places like San Francisco that we get earthquakes. We get earthquakes in the UK. Here's a map showing a lot of earthquakes in the UK. Again, the bigger the circle, the bigger the earthquake. And the largest earthquakes in the UK can be up to around about magnitude 6. And these two also line up along faults. There's the Great Glen Fault, which runs through Scotland, that's still moving, and the Pennines Fault that runs down the spine of the country, and a vast number of smaller faults in the UK. Now, the largest of these earthquakes, magnitude 6 earthquakes, if one of those was to occur in the UK, it could cause significant damage. So if you were an insurance company and you wanted to know how much to fleece your customers for their household insurance, you need to know what the likelihood of the next magnitude 6 earthquake is in the UK, because it's going to cost you tens of billions of pounds. It's a really good example of how geoscience is behind an awful lot in the modern world, and we never even realize that it is there. Now, geology and geophysics kind of come together, those approaches, the fundamental calculations and observations, they come together in planetary science. And this is a really good example of how these can come together in studying other planets. So this is a photograph from one of our third year independent mapping projects, which was conducted on Mount Etna. And it shows a hornito. This is a type of small volcano, and these are sitting on lava flows on Mount Etna. And we can tell that it is a hornito because there's lots of lava, cooled lava coming out of this central cone. And when we look at the lava, we can tell which direction the lava was flowing in by these flow ridges, these pohoihoi flow ridges. And if we fly a drone over the top of this hornito, which we did in the field with students, and we can see all the lava flows are pouring away from that central summit. So this is a small volcano sat on top of a lava flow, and these volcanoes are known as hornitos or rootless volcanoes. So we can use some geophysics to try and understand how that volcano formed, because in our lava flow we have a cooled solid crust and then the magma flowing downhill beneath that crust. And our observation indicates that our hornito is sitting at the bottom of a slope. And it should be clear why the hornito is most likely to form at the bottom of the slope, because as the magma travels downhill, the pressure will increase the most at this location. And if the pressure exceeds the strength of the rock, it can break through that crust and erupt and make a hornito. So we can use some simple physics to calculate how much pressure is increased by that downhill flow of magma. And here, the strength of the rock is this term, is S. And we can rearrange that equation for the strength of the rock. So we've then got a relationship between the density of the lava, the local gravity, and the hydraulic jump, the drop down which that magma has flown. So if then we use some observations, for example, of hornitos on the surface of Mars, for example, on Olympus Mons, and some of these little cones you can see here are hornitos, then we can use those observations and this equation to try and calculate the strength of magma of that rock on the surface of Mars. So without ever visiting Mars, by applying this fundamental model and our observations, we can make measurements on the surface of Mars just on the strength of rocks. So planetary science really is a combination of different approaches. But really the reason that geoscience is more important today than ever before is not really about space, it's about our own planet. Because there's now 7 billion people on planet Earth. And it wasn't long ago that it was 6 billion people. The United Nations estimates that the planet's population will plateau at around 12 billion people. And every one of those people wants an endless list of commodities, mobile phones and cars and washing machines and fridges. You know, the list is almost endless. And that all requires resources. And our planet's resources are finite. Because essentially, if you can't grow a resource, you have to dig it out of the ground. Whether that's an energy resource, a resource for pharmaceuticals or manufacturing, or for building, if you can't grow it, it has to be mined. And then there's some resources that we in this country don't tend to think of as resources. Water is an incredibly important resource. And actually, in some parts of the world, it poses a significant supply problem. So, for example, in India, over the last few years, there has been a water crisis in Delhi because there just isn't enough for the population and for industry. And in managing water resources, you need to be able to search for water beneath ground, for aquifers, and also manage water on the surface. And if you're going to build structures like dams, you need to know an awful lot about the engineering properties of the rocks you're building them on. But perhaps the most important aspect of earth science at present is in tackling global warming. So the reason I'm showing this picture is it makes one thing absolutely clear, and that is that we have caused global warming. So this shows the amount of CO2 in the atmosphere. These are modern day measurements of the atmosphere, and these are measurements of gas within little bubbles within Antarctic ice. And as you can see, there is a sudden increase in atmospheric CO2 beginning at the Industrial Revolution. We have very clearly caused global warming. And it's technology that will probably save the planet. We need to change our high carbon lifestyles, our high carbon civilization, into a low carbon, renewable civilization. So we need to generate energy through solar energy and through wind power, and then use that energy in electrical devices. So electrical heating, electrical motors, recharge, and these all require things like rechargeable batteries. Now, who thought that we would ever see a situation where up to 75% of power in the UK is generated by renewables? Or that we would stop using petroleum cars. So petroleum cars, diesel cars, will no longer be for sale after 2030. And to do this, we need resources. We need new resources. For solar cells, we need things like phosphorus and boron and rare earth elements. And you might have guessed, because they're called rare earths, there's not a lot of them. They're very difficult to find. We need neodymium for magnets. In most of these wind turbines, there are these incredibly strong permanent neodymium magnets. And then in using that power, we need conductors like copper, gold, and silicon, and lithium batteries. Now, to give you an idea of the magnitude of the problem, the yearly demand for copper is around 12 million tons of copper per year. Now, if you find it difficult to visualize 12 million tons of copper, it would be enough to fill up the Empire State Building 3 times over. So we have to find this copper every year, and we've been digging up copper for over 3,000 years. All the easy to find copper went a long time ago. Unless we find 12 million tons of copper per year, industry stops. We can't make anything. And you can say goodbye to modern day civilization. So ironically, it may well be mining, it may well be the resources that we need in order to run the modern world without carbon that saves the planet. Now, I think if you talk to most of our students, you will find that most of them aren't doing earth science for a particular career in mind. In fact, most of them, I think, are pretty interested in saving the planet, but overall, they've chosen earth science, earth and planetary science, because of their enthusiasm for the subject. And my advice to you is you are going to be doing a degree for 3 to 4 years. Read around the subject, make sure you are interested in it, that it will enthuse you. Now, luckily, earth science is such a diverse subject. It includes maths and physics, chemistry, biology. You can study fossils, dinosaurs, volcanoes, earthquakes, outer space meteorites, planets. There's a lot of things there that everybody should be interested in. But I think if you talk to the students, especially the geologists and most of the earth and planetary scientists, one of the highlights of their degree is fieldwork. It's actually getting outdoors and getting hands on rock and doing your own interpretations, applying your knowledge. Because we believe that a good geoscientist, a good earth and planetary scientist, should be able to do geology. They shouldn't just know geology. Now, of course, over the last couple of years, getting out into the field has been a little bit tricky. We all kind of have missed it a lot. Now, luckily, we have been out in the field again. In autumn, we took a whole bunch of field trips out, and we are expecting to get out into the field again in the spring. But one of the benefits of the endless lockdowns and not being able to take large groups of students traveling has been that we have been forced to develop new technologies. So we've developed virtual field trips, virtual as these remote learning experiences. And this is an example of one of these. This is a virtual landscape that you explore in the computer, very much like a computer game, except the objective is to learn about the rocks, is to make interpretations by studying the rocks. And actually, this is based on northwest Scotland. It's very accurate. There's over 1,000 outcrops in there, and it reproduces 9 square kilometres of the Northwest Highlands. Now, although we hope not to have to rely on these anymore, and that we actually will get everybody out into the field again every year, they provide us with a new way of teaching. So we can transport our students at the click of our fingers to Santorini, or to the top of Mount Everest, or to Mount Etna in Sicily, or indeed to the surface of the moon. It provides us with a whole new way of allowing you to experience earth and planetary science. I suspect, however, that the students also enjoy field trip because it gives them the opportunity to socialise and enjoy themselves. Here's a photograph from Sardinia a few years ago, and you can see the students are happily enjoying themselves on the beach after a long, hard day. I would point out this is most likely a bottle of lemonade. So the students enjoy it, although these days the staff find it particularly difficult to keep up. So I thought I'd end at a beginning, because a geoscience degree, whether it be geology or geophysics or earth and planetary science, could be the start of a career. And a geoscience career can be a real adventure. So, for example, when I was sat where you are, I had no idea that one day I would be going off to Antarctica, driving around on skidoos to collect meteorites with the US Antarctic program. Geoscience is an incredible subject because it can take you to some of the most amazing places and the best experiences that our planet has to offer. Thank you.